In this section, we talk about higher order derivatives, which may sound a little intimidating. It's really not. It's not bad. It can be bad if, depending on the type of function we're looking at. But a higher order derivative, that just means we're taking derivatives of derivatives. So what we've been doing so far, we're now going to call those first derivatives. That is, the first time you take a derivative, it's called the first derivative. Then if you take the derivative of that would be the second derivative. And then the derivative of that would be the third derivative, and so on, just depending on what it is you're trying to do. We do use the second derivative for some things that are coming up a little bit later. So there will be a use for these, and you'll see that actually in a few minutes. All right, so notice the notation. So you can have that double prime, y double prime, or the second one, that's the second derivative of y with respect to x. And the third notation will be, okay, let me turn my volume down. That would be the second derivative of f of x with respect to x. All right, so even though, it's got that dx2, looks like a square, but it really stands for second derivative. All right. So we want the second derivative of the function. What is going on here? I started to use f prime, but it's y, so pretty much the same thing, but all right. So I'll put y. Let me start over. Let's get what we now are going to call the first derivative, y prime. So I'm hoping you're pretty good at this by now. Taking the power 3 times the coefficient 12, and then subtract 1 from the power. For 9x squared, we'll do 2 times 9 is 18, subtract 1 from the power is x. And then 7 is a constant, its derivative is 0. Okay, so that's nothing new. We're just now calling it a first derivative. Now we take the derivative of that, and we're calling it the second derivative. So again, the power of 2 times 12, 24. Subtract 1 from the power, leaves me with x. And then for 18x, remember, when it's x to the first power, the derivative is simply the coefficient, and we're done. All right. Okay, for problem 2, we want to get the first 4 derivatives of the function given. So here's the first one, f prime of x. 3 times 5 is 15. Subtracting 1 from the power gives me x squared. 2 times 3 is 6. Subtracting 1 from the power leaves x to the first. And for minus 9x, the coefficient is minus 9. And then the minus 6, that's your constant, its derivative is 0. So that's your first derivative, nothing new there. Second derivative is the derivative of that. So 2 times 15 is 30. Subtract 1 from the power, leaves x to the first. And then for 6x, the derivative is 6. And minus 9, constant, this derivative is 0. All right, now for the third derivative, starting to look a little messy. For 30x, the derivative is 30. 6 is a constant, so its derivative is 0. And then for the fourth derivative, have 4 little prime marks. So 30 is a constant, and its derivative is 0. That's it. All right. So hopefully not too bad, you know, until we get to, oh, I really do that. We're probably going to change that one up. For problem 3, it says find f double prime of x, so that's the second derivative. Remember, for my radical, I do have to rewrite that without a radical. So that's 4x plus 1 to the 1/2. All right, for my first derivative, this is the chain rule that we talked about last time, because it's a function raised to a power. All right, so the chain rule says we'll take the power, which is 1/2, in front, multiply it. Repeat the function, copy, however you want to say it, copy the function, subtract 1 from the power, and then multiply by the derivative of the function. All right, so here's the chain rule. The derivative of u to the n, where u is a function of x, n times u to the n minus 1 times the derivative of u. That's the chain rule from last time. All right. And we also called it the extended power rule because the first part of it looks just like the power rule, but because what's raised to a power is a function of x rather than just the single x, we have to do that part at the end, which is to multiply by the derivative of the function. All right, so I'll keep going. 1/2 minus 1 is negative 1/2. And then the derivative of 4x plus 1 is 4. And you want to simplify here because you're not done. You got to get the derivative of that. So we want to go ahead and multiply the 1/2 and the 4 to make it as simple as we can before we get the next derivative. All right, so 1/2 times 4 is 2, and that's my first derivative. All right, now for the second derivative is the chain rule again, because we still have a function raised to a power. So f double prime. Now I've got a 2, the coefficient of the function, I just hang on to that. I multiply by the power, which is negative 1/2. keep the function, subtract 1 from the power, and multiply by the derivative of the function. So you may or may not have had a chance to practice the chain rule from last time. But hopefully you remember, what we talked about. Okay, then I can multiply 2 and negative 1/2, that's negative 1. And when I subtract 1 from negative 1/2, that's negative 3/2. And then the derivative of 4x plus 1 is 4. The only other thing I'm going to do here is multiply negative 1 and the 4, which gives me negative 4. Again, we talked about, last time we talked about the algebra that's involved with a lot of these problems. So for me, that would be fine right there. Okay, that would be an okay answer. If you're asked to simplify, because honestly, I never know what they're going to do. And you can always, if you do view an example, you can look at what they did, and at the end you can see how they left the answer. That's probably what I would do. So to simplify this, there are two things we do, but the first thing we have to do is make the exponent positive. So that means put 4x plus 1 to the positive 3/2 in the denominator, and then I can multiply the negative 4 and the 1 together. And so I'm just going along with the fact that the original problem had a radical, so I'm writing the answer with a radical. So that's the second thing I did there. Okay. And, honestly, that wouldn't be my favorite kind of question to put on a test. Typically the homework is probably more involved, on a general basis than what I would put on a test. Okay, I'm going to do problem 4, but notice I'm taking away the exponent, because that was the one we looked at last time, which was a combination. This would be really messy. That would be a combination of chain rule and quotient rule. So I'll let's take the power off, and so it's just a quotient. So let's just write it as 2x minus 3 over 4x plus 5. All right. So this is a quotient, which means for the first derivative, y prime, I'm using the quotient rule. For the derivative of a quotient, the denominator times derivative of the numerator times, then you swap them around, all over denominator squared. Okay, so I'll start with 4x plus 5 times the derivative of 2x minus 3. I don't know what, that's a minus right there. I don't know why I put that dot. Minus Now we swap them around. The derivative of 4x plus 5 times the numerator 2x minus 3, and that's all over the denominator squared. Excuse me. All right, then I do the two derivatives that are inside of the quotient rule. So the derivative of 2x minus 3 is 2. On the other side, the derivative of 4x plus 5 is 4. All right. And be careful about any temptation here to cancel some stuff out. Remember, we never do anything with that denominator. We just keep the denominator all the way to the end. All right, so now I'm working on simplifying the numerator. Which means remove the parentheses, and that's going to be distributive property. So 2 times 4x is 8x. 2 times 5 is 10. Then the minus 4 go together. Minus 4 times 2x is minus 8x. Minus 4 times minus 3 is positive 12. And that's all over that denominator squared. Now notice that the 8x and the minus 8x, those cancel out. They add up to be 0. We can add 10 and 12 is 22. All over that denominator squared. All right. So that's your first derivative. Now we want the derivative of that as our second derivative. Well, you could use the quotient rule, but I would advise you to use the chain rule. If you look at that carefully, you could rewrite that as, let's see if I've got room. Bring the 4x plus 5 out of the denominator and make the exponent negative. And to me, that's easier than using the quotient rule. If you wanted to use the quotient rule, you could, but I prefer the chain rule. All right, so now for the second derivative, like I said, I'm going to use the chain rule because I wrote my function that way. So for y double prime, hang on to the 22, multiply by the power of -2, keep the function, subtract 1 from the power, and then multiply by the derivative of the function. And then just keep going. That's -44. -2 minus 1 is -3. And then the derivative of 4x plus 5 is 4. And then we're just going to simplify it a little bit. I'll take the 4 over and multiply it by the -4, 44. I'll put the 4x plus 5 cubed in the denominator to get rid of the negative exponent. And then that's what? -256 over 4x plus 5 cubed. No, it isn't. 176. All right, 176. Okay. All right, so any questions on that? Like I said, you know, with polynomials, it's not difficult. With square root functions or rational functions, it's more complicated because those functions themselves are more complicated. All right, let's see what's next. Okay. So next we're looking at a couple of applications of second derivatives. And one of the first ones that we talk about is acceleration. So there's a lot of stuff in there. Velocity is, let me back up. Let's say given a distance function and I think we call it S. Velocity is the first derivative of S. And acceleration is the second derivative of S. I think that's what it says in there, but that just kind of cuts to the chase. All right. So velocity, remember, derivative is a rate of change. So when you say you're driving at 30 miles per hour, that's a rate of change. That's by how much your distance is changing with respect to time. 30 miles per hour. Every hour driven, your distance changes by 30 miles. And then acceleration is, well, it's also, acceleration is the derivative of the velocity. So it's the rate of change of your velocity. All right. So that is one of our popular applications of second derivatives. Okay, so in this problem, we have a function that's a distance function. So the particle travels according to the equation where S is the distance in feet and T is the time in seconds. So again, notation, and specifically, you know, with these real problems, it's good to think of the derivative with this notation because it shows you the relationship. You know, the rate of change is the change of something with respect to something else. So this is the derivative of distance with respect to time. All right, so 100t, derivative of that would be 100. For minus 16t squared, I'll multiply 2 by 16 is 32. Subtract 1 from the power gives me t. All right, and then for 200, that's a constant, and that's it. Okay, so that's the function that describes the velocity, and the units involved here would be feet per second. Okay. Now, and you can write this, v for velocity. The function that describes the acceleration is going to be the derivative of the velocity which is the second derivative of the distance. And remember, that's just our notation. That's the second derivative of d with respect to t. Second I don't know what I think I missed. Second derivative of S, I think I said D, with respect to T. That's a 2. Okay, so we're just getting the derivative of that. That's pretty easy. The derivative of 100 is 0. And then the derivative of minus 32t is just minus 32. So that's your acceleration. All right. And the units, that we would use to describe that would be feet per second squared. Okay, that's kind of strange, I know, but it's because you're talking about the change in speed, or how the velocity is changing, would still be a number of feet per second squared. All right, so that's the acceleration. The fact that it's a constant, negative 32, that would tell me that this particle is actually decelerating at a constant speed. All right, so that's like I said, a pretty popular example of a use of a second derivative. In problem 6, okay, in problem 6, we have a function that gives the consumer price index of an economy, where t equals 0 corresponds to the beginning of 2000. So the first derivative of this function that's confusing issue. Let's just say the first derivative of this function measures the inflation rate of the economy at, well, at t equals c, but just, so the derivative, the consumer price index, tells something about the economy, and the rate at which that is changing, that's how they compute inflation. Okay, so I'm just gonna again write it a little more succinctly. All right, so the derivative of the CPI gives the inflation rate. Okay. All right, so just forget about all the stuff in there. We'll talk about that. Let's go ahead and do part A, which is to find the inflation rate at the beginning of 2006, which is t equals 6. I have a graph of the function because I'm going to talk a little bit about what this means from our graph, so just hang on to that. So basically, we need the derivative of c. So maybe I'll just write that one out instead of doing that mentally. So I'm hanging on to the negative 0.2, and then the derivative of t cubed is 3t squared. And then for 3t squared, I'm keeping the 3 times the derivative of t squared, which is 2t. And then for 100, that's a constant, the derivative is 0. And then multiplying to simplify gives me that. Okay, but they're question is, what is the inflation rate when t is 6? So that's the derivative evaluated at 6. So I'm just going to substitute, it's a lot of 6's. I'm substituting 6 in there and just bringing out my calculator. And I get 14.4. All right, so that's the inflation rate. If this is an accurate function. All right, now let's look at the graph. This is the graph of the CPI. And we're looking at what's happening right here at t equals 6. Okay, so we're right there on the, well, you'll see in a second. You might be able to see there's something going on there that we'll be talking about in a minute. It's actually called an inflection point. But this says, show that inflation was moderating at that time. Moderating means slowing down. So basically, what we're talking about here is the rate of change of the inflation. All right, the rate of change of inflation is the second derivative of inflation. Sorry, second derivative. Back up. That's the first derivative of the inflation. All right. So the rate of change of inflation tells us whether I don't want to word this. Tells us whether inflation is increasing or decreasing. All right. So it says show that inflation was moderating at that time. That's going to involve the second derivative of my functions, the CPI function. So I'll go up, right at the top of my screen is the first derivative. Now I want the derivative of that. The negative 0.6 times the derivative of t squared is 2t, and then the derivative of 6t is 6. And then simplifying gives me negative 1.2t plus 6. All right, and then again, at t equals 6, we're evaluating the second derivative. So I'm substituting 6. I think that's negative 1.2. All right. So the fact that that value is negative, that tells me that the inflation is decreasing. All right, so because this value is negative, tells me that the inflation is decreasing, slowing down, same concept. All right. Okay, so let's just look at the graph for a minute. What we're going to be doing next, in the next chapter, is applications of derivatives, which we've already looked at some of those, and this is an application of a second derivative. We're going to see, let's see if I can manage this, that, sometimes I just miss the good old days of the chalkboard. Oh, y'all ever been taught on a chalkboard? Come on. My computer is changing at a slow pace. All right, so we're gonna see, change to green. We're gonna see at this particular place right here at t equals 6, that's what we're gonna end up calling an inflection point. Just give me a little glimpse into the future. And what we're going to end up saying is that this red piece of the curve is what we call concave up, and the green piece of the curve is concave down. And that's actually has to do with the second derivative. All right, so I'm just kind of sharing with you what's coming. And that's why this particular point is going to be important, because it's the place where the concavity changes. All right, so we have a name for that. Anyway, are there any questions? So we're basically talking about higher order derivatives, and the examples, the applications that we do involve second derivatives. All right. All right. Anything, question? No. Okay. So I had mentioned last time that I knew that this section wouldn't take too long, and that it would be a good idea to go ahead and start in the next section, because there's a lot to explain there, and I just thought it'd be good to go ahead and start on it. Your homework on this isn't due till, you know, Sunday, a week from this Sunday, so I just want to go just do a little bit in here, so we have, you know, enough time to talk about it. So, like I said, we move into chapter 2, which is applications of derivatives. And in calculus, when we're talking about derivatives, there are always two, well, I think of two different types of applications. One is with the graphs, so that's kind of the math part of it. And then I'm going to put applications here. That's not examples from life, I guess. Okay, so when we, like I said, when we talk about applications of derivatives, we talk about what derivatives can help us with graphs, and then how does that help us with some, you know, examples, applications from life. All right. So the first thing I want to talk about is, or just an algebra introduction. Consider the function. Let's see, I don't have my calculator going. Consider the function negative x squared plus 6. Let me go ahead and pull up my calculator. I don't actually need my calculator, just give me a better picture. So hang on 1 second. Anytime now. Here it goes. All right, so I'm just, like I said, so I have a nice looking graph. I'm just putting this in my calculator. I'll just move this number. All right, so there's the function negative x squared plus 6. The vertex of this graph is at the point 0, 6. The domain is all real numbers. You know, just reviewing some stuff. The function is increasing on the x interval. So basically, remember that a parabola is symmetric. You can like slice it down the middle. The left half of this parabola is increasing. The left half is increasing. The right half is decreasing. But the way that we write this mathematically is by describing the part of the domain, which is an x interval. So we would say that the function is increasing on the interval from negative infinity to 0, and then decreasing from 0 to infinity. All right. And you talked about this kind of stuff in algebra. Well, it turns out, do I need to look at this chat? Oh, okay. Hey guys, I'm sorry. In the future, just unmute yourself and speak up, because I forget that I forget that if I change screens, I have to physically do that. Okay, are we good now?
Yes, ma'am.
Okay, sorry, but thank you. So this is what I've been talking about. I graphed the function negative x squared plus 6. We talked about, I talked about the vertex being at the point 0, 6, and that the function is increasing from negative infinity to 0 and decreasing from 0 to infinity, and that those are x intervals, which are part of the domain. All right. So it turns out that calculus can help us with this. And let me back up or remind you here, a relative maximum is a point on the graph of a function where it changes from increasing to decreasing. So let me just draw this thing right here. This point is what we would call a relative maximum. And this one is a relative minimum. All right. The way that we define, I mean, you can see it on the graph, it kind of makes sense, but the way that we define that is what's written here. The relative maximum is where the function changes from increasing to decreasing. And then your relative minimum is where it changes from decreasing to increasing. All right, so those are your definitions. Well, it turns out that the derivative tells us exactly where those places are going to occur. Okay, exactly where they're going to occur. So what I like to do here is just hop into an example. Boy, my spacing is messed up here, isn't it? What's going on? Okay. So yeah, there's all that wording. I'm just gonna go over to the first example and just show how this works. And you have those steps written above to refer to. All right. So given this cubic function, we want to know where the function is increasing, where it's decreasing, find the relative maxima, that's plural of maximum, minima, plural of minimum, because you can have more than one. All right. Now, with our calculators, you know, this is going to be a little tricky on my part, because with your calculator, you can probably find most of that information. Just by graphing it. So I know you can't see what I'm doing, but I'm just typing this function in my calculator. -2. Just fixing up the window, so all right. Great. That's not really- Oh, great. Well, let me try that a different way. Okay, I do not know what is going on here. Let me try pasting this up. Try it again. Okay, there's the graph for problem 1. That's what I was, for some reason it wouldn't paste below. So that was 2/3 x cubed, right? Minus 2x squared minus 6x minus 2. Let me see if I got all that right. Yeah. Okay. So one might say, hey, there's your relative maximum and there's your relative minimum. And, you know, your calculator has features that would allow you to compute exactly where those are. All right. And I can't argue with that. I mean, that's fine. the problem is, what if we have a function whose graph is hard to read, or, you know, we can't really see what's going on? Calculus that takes that away from us. You know, calculus tells us exactly where to look for these numbers, relative max, relative min, okay? So don't discount this and say, well, I can just use my calculator, because once, you know, when we get to problems like, this is messed up, maybe like number 3, wow, this is really messed up. I need to fix this document. Problem 4, you don't want to have to rely on a graph because they're not as easy to read. Let's see what this is doing. Wow. Document has some formatting problems. All right, so what I'm going to do is go through how we use calculus to help us find the answer to the question. The first thing we always do is find the derivative, the first derivative. All right, so f prime of x. All right, I'm keeping that 2/3. And then the derivative of x cubed is 3x squared. And 2 times 2 is 4. Subtract 1 from the power gives me x. And then the derivative of minus 6x is minus 6. The constant is 0. The 3's cancel. So my derivative is 2x squared minus 4x minus 6. All right. We set the derivative equal to 0 and solve for x. To find what are known as the critical values. They're called critical values because they're critical. Turns out that's exactly where we would look for a relative max or relative min. So now I have a quadratic equation that I need to solve. I'm going to solve it by factoring. But, you know, knowing that some of you maybe don't have a strong factoring background, remember there are ways you can do this on the calculator. I think I talked about them. I know I talked about them somewhere along the way, but I'll show you again in just a minute. So by factoring, you know, if you're good at factoring, and if you're good at algebra, you have a big advantage. I mean, there's just no question that, you know, algebra is important in calculus, but, you know, I'll try to give you other ways. Okay, so I factor it, and then once it's factored, I set each factor equal to 0 and solve for x. All right. So for example, a question on the test may be, for this function, what are the critical values from the first derivative? All right, in other words, I'm going to kind of make sure you know how to use this method rather than just relying on the graph. All right. Now, I'm going to go to my calculator. Now I showed you, some of you have, if you have this application on your start to say your phone, but on your calculator, If you have item 9, poly simultaneous, it may or may not say a 2, that doesn't matter, but poly simultaneous is a very nice feature. It solves a polynomial equation. So I got that, and I went for polynomial root finder. I press enter. This is a second degree equation, so that's good. Then I go to next, and I just type in the coefficients, which it was 2x squared minus 4x minus 6. Minus 6. Okay, so I just type it in the way it looks on my paper. I need to solve next, which is alpha 5, the F5, and there are the solutions. All right. I'll probably come back and paste these screens in. I'll go ahead and pop this one in, but I'll come back. I'll come back and pop them in because this thing is being weird with this particular page. So I'll do that later. All right. So those are the same numbers I got on my paper, my document. Let me go back there. All right. So or use under your apps key, poly simultaneous, polysmelt, or you can use the math solver. I won't show you that yet right away. I want to go ahead and try to at least finish this problem. Okay. All right. So I've done the first thing, which is to find the critical values, and so I'm up here. Formatting is really messed up. Okay, so I'm determining where my function is increasing or decreasing. So I'm right here. All right. So that's what I've done. Find all values of x for which the derivative equals 0, or the derivative is undefined. That doesn't happen with the polynomial functions, but these are the critical values. Give them the name. All right. Then it says identify the open intervals of the domain determined by these values. Okay, so what do I mean by that? What I'm going to do now is draw a number line that indicates the domain. The domain, this is a polynomial function. That's why we talked about domains in the beginning. The domain is all real numbers. So on a number line, it is the entire number line. I take the critical values and put those numbers and only those numbers on the number line, put them in order, of course. And then I always draw a line under those to represent the 3 intervals that I've created. The 3 intervals are numbers to the left of -1, numbers between -1 and 3, and then numbers to the right of 3. So please don't mess up. All right, so these are the intervals of the domain. All right. The next thing I do is pick a number from each interval. That's called a test number. It can be any number you want as long as it's in that interval. I always recommend, using the simplest number you can think of. All right, so to the left of -1, I would pick -2. Let me put this test number from the interval. Between -1 and 3, I would pick 0. And to the right of 3, I would pick 4. All right. Those are my test numbers. Now what I'm going to do is substitute the test number into the derivative, the first derivative, which is 2x squared minus 4x minus 6. Now, I'm going to use my calculator to do that because I can and because it's faster. All right, so now I'm putting the derivative in my calculator. I'll go over to my calculator and share the screen. And like I said, I'll paste these equations in after class because I know there's a formatting issue. All right, there's the derivative. Hopefully you set your table the way that I asked you to set up your table so that, and I had you go here to second window, the table setup, and have the last 2 lines set up the way I have it. With independent variable on ask, that's your X, and dependent variable on auto, which is your Y. So this allows you to put in whatever number you want for X, and it will automatically compute Y. All right, so I'm now going to put in my test numbers, which were -2, 0, and 4. Let me just see. I don't know if I can copy that on my document. I'm going to try. It didn't work. What's going on with this thing? Okay, I got it. All right, so I'm going back to the document. I know I'm running out of time, which I figured I would. But the hard part's over. Okay. All right, so this is, like I said, my test number went in here. This was my derivative, my first derivative. So it turns out the sign of the first derivative gives me the answers that I need. All right. So when I substitute the test number in the derivative, I'm really only interested in whether the function value is positive or negative. All right, so let's look at the -2. When I put -2, the derivative is 10, 10 is positive. When I put in 0, the derivative is -6, which is negative. And when I put in 4, the derivative is 10, which is positive. Those signs right there tell me everything I need to know. All right. For example, I'm going back up to all right, I'm going back up to here. All right, so I'm talking about this step 2. This is what I've just done. I found a test point in each interval, determined the sign of the derivative in that interval. If the derivative is positive, then the function is increasing on that interval. If the derivative is negative, then the function is decreasing on that interval. This is what I call the power of calculus. We now know, without a doubt, where my derivative is positive, the function, the original function, is going to be increasing. Where the derivative is negative, the function is decreasing. And we usually indicate that by what I'm doing right here. I'm putting some little signs, positive and negative signs, up on the number line. And the thing that I just boxed, that's called a sign diagram. If you took college algebra, you probably did something like that. But that right there tells me everything I need to know. The intervals, so let's write it up. So my function, which was 2/3 x cubed, I've forgotten it now, minus 2x squared minus 6x minus 2. That's the function we're talking about. It is increasing on the intervals negative infinity to negative 1 and 3 to infinity, and it is decreasing on the interval -1 to 3. And remember that, I mean, that we're talking about an interval. That's not an ordered pair. That's the interval from -1 to 3. Okay. So there's a little more to it, but it's 12:15, and I don't want to keep you past class time. So I'll stop with this. When we come back on Tuesday, you know, I'll just kind of review this and finish up the problem and go from there. Okay, but I wanted to at least get started in this section. As you can see, how long it took me just to go through the first one, you know, explaining it and so forth. All right. So I'm going to stop